Hello, guys. Today I'm going to talk to you about obtaining and organizing big data. So this whole thing started during the break when I was being curious about what is this thing with data science. At the end of the day, I ended up collecting data, which ends up being the most bureaucratic and time-consuming part of data analysis. So I used a flight ticket data set, which is compiled by the Research and Innovative Technology Administration together with the Bureau of Public Transportation. And this data set gives you data on flight tickets with price, destination, and location for the last 15 or 20 years. You have around 7 gigabytes per quarter in big CSV files organized per quarter. And in total, there's more than 700 million records. So it's a pretty cool data set. And the first thing I try to do is automatize or semi-automatize the process of bringing this data. I wouldn't suggest doing this on your computer, but even if you do it on something like a web service, the same kind of iterative process could apply. So CSV files look like this. And here, that's an example of, I think, the quarter of 2004. And here you see details about a specific ticket. These two tickets belong to the same itinerary. That's the 2004-18 is the itinerary ID. And then it has two different coupons, one from New Mexico to Atlanta, the other from Atlanta to New Mexico. And anyway, the details of the data set here don't really matter. The issues are that how do you automatize collecting this? The first problem is how do you even open these files? They're 5 gigabytes, they take lots of memory, it takes lots of time. So Unix is a really cool thing, and it's your friend here. So this is a simple Unix script that creates a handler to a file, and which is actually a stream to a specific file. And you can create this simple Unix script that reads a file 5 lines at a time. So if you see that running, it looks like that. You run it like this, and you don't have to open the whole thing. You just hit 5, 5, 5, so you have an idea of what's inside your data set, which is the first useful thing to have. Now, you can also use another command called head that gives you the initial part of the file. Now, the other thing is how do you download them automatically? Again, manually, you would go to one of these forms, select the fields that you want, click download, and you would have to do that repetitively. Each download, you wait until the zip file is being generated, and then you store the zip file. With curl, you can do this automatically. You go to your network panel, you right-click, and you copy your request as a curl. And now you get something ugly looking like this. That's the curl generated. You have the URL, a bunch of headers, a cookie, blah, blah, blah. And at the end, you get the exact SQL statement that this choice is producing. And that's where you can do the hack. At the end, you can just change the one here in 2016 to whichever quarter you want. And this you can do again with a really small Unix script. There is a first issue. If you run that curl file, you actually don't get the zip file yet. You get a response that the object has been moved that includes a link to the generated zip file. So curl can solve this too. And that's a script that does it for each year from 2004 to 2015, and each quarter from 1 to 4. And that's a curl that says -L, which means follow the generated link. You give the headers you got and the cookie you got from the previous slide. And then the only thing that you change is this data parameter. You parameterize the year and the quarter based on your loop. And you tell it to put that in a zip file with a specific name. And here it is. 5 lines of code brings you some equivalent of 100 gigabytes of data. So it's pretty cool. Now, when you bring all the zip files, you want to unzip them. Again, you can write a loop using bash that tells take each zip, unzip it into that CSV file, and then you can use sed, which is a classic regular expression Unix program that effectively takes that file and removes the headers. Usually these files have some headers that say itinerary ID, market ID, and all that stuff that you don't want into the database. So this piping here fixes that problem, and you can also say remove all the commas from the end of the line, because that's something that also Postgres doesn't expect. So you can do, as you bring them, you can also do some simple regular expression editing on the fly. So, and now you can do stuff. Now you can, that's something I generated with R. These are the most popular destinations from LaGuardia for the first quarter of 2016. And that's the first sanity check of your data, because you can go to Wikipedia and see which are actually the most popular destinations. And it works. Here you see this 25,000. It's actually 250,000, because my data are a sample of 10%. But otherwise, the data are pretty accurate. So once you have that, that's the first sanity check that you can do. Now, the problem is that with CSV files, you cannot really search. You cannot really do collective queries in different years. You need a database. So the other headache is, how do you organize the stuff from CSV into a Postgres database system? First of all, it seems one approach would be, here's a big table. It's called tickets, and it has all the tickets that I found. There are not many. There are relations, but I'm not going to talk about relations. But that's the first approach to bring the data in. That causes a big problem, because if you want to search for things like based on state, you want to index these tables. And indexing 50 gigabyte of data will produce another 15% size of indices on top of it, right? Because hashing has to be they have to be hashed, and the buckets of this hashing function will be larger and duplicate all the time. So there is a cool feature in Postgres that's called partitioning. And you can actually, the idea is this. That's something unique to Postgres, and it's pretty cool. Instead, you create one big table so that you're able to insert data to it and query it. So you can query all the tickets collectively, but nothing goes into that table. It's like a virtual class, right? So you create that table as a virtual thing, and then for each quarter, you create a child of this big table, which I call market quarter for each year and for each quarter, to which I check certain properties, right? For each table needs to have all its entries in the specific year, and the quarter should be the specific quarter. And here's the trick. It inherits from the market ticket. So all these subtables have the same structure of the initial one. And now inside here, you can add any kind of index you want, and things are feasible. This comes together with to finish this partitioning and actually make the original table virtual. You need to say that every time you insert to the initial table, you actually route this insertion to one of the appropriate subtables. And that looks a little bit ugly, but it says that effectively every time you insert to the market ticket, execute the instruction that inserts to the appropriate subtable. Right? This way, the big table ends up having 0 rows, but you can treat it as a proxy to all your tables. So you get the best of both worlds. The other good thing is that your ORM, if you use Sequelize later on, doesn't even have to know about the subtables. You just say insert to the market ticket, and then Postgres takes care of the whole rerouting idea. Okay, so the other trick is once you create that trigger, you put it before insertion on the market ticket, and that does exactly the job that I was just explaining. So now you have all these tables. They're nicely organized. You can query them as if they're one big table, but you have to actually take the CSV files inside these tables. And there are some things that you want to check before you actually validate this data. You want to check, are the primary keys that are said to be primary keys actually unique? Or are things like the distance group column actually between 1 and 25, right? You cannot really do that parsing 100 gigabytes of CSV files. It will be very slow. So one way to do it is use Postgres again. So you create for each quarter a temporary table. You insert the CSV file under all these checks. And if these checks pass and this insertion doesn't break at any point, then you insert the data from the temporary table to the market ticket table. And that's a standard iterative process to validate CSV files before you actually put them in. And the coolest part here was where I found this PG pool library. The PG pool library actually gives you connections to the Postgres server, but it gives you multiple threads. And it plays very well with partition data, because now you can say, OK, take the CSV file, put it in that quarter. In parallel, take this other CSV file and put it in that quarter, and in parallel, do that. So if you have partitions, then it's a really nice tool. It plays well with generator functions and yield. And one good thing about this is that it permits asynchronous code that has some sequential nature in it to feel natural. And you can write for loops, whereas with promises, it becomes a thing you have to say for each. So that's how it looks. Effectively here, I have for every year, I created a process and each process runs independent on a different client. Each client creates the raw ticket market table, seeds it from the CSV files, and if that succeeds, it inserts it to the particular subtable of the partition. I'll put up the code on GitHub, and you can have a look at it. I think PG pool was a really, really interesting thing. Last thing, what is wrong with Sequelize? In a nutshell, the fact that when you query a table and you want to get all the results of a 5 gigabyte table inside another table, that creates a huge array in the memory, and my computer crashes. In opposite, you would like to have an ORM that gives you a stream out of a query, and if you don't have that, you use directly with PG Client in a lower level. Later, you can get all the models you want from Postgres using a nice tool called Sequelize Auto. Thank you very much for your time.